Welcome to section 13.2, Patterns and Surface Area. Here are the topics and understandings, grade level, and concepts and vocabulary. So in the previous section, we saw that important characteristics of polyhedra are their faces, edges, and vertices. So three-dimensional shapes have essential characteristics that are two-dimensional, one-dimensional, and even zero-dimensional because of the points. So this is a short section, but we're going to focus on two-dimensional aspects of solid shapes, their outer surface. And we also consider other two-dimensional aspects of solid shapes, cross-sections, and shadows. So one way to make a solid shape is to make a pattern on paper for its outer surface, cut out the pattern, fold it, and join the edges. So making a shape in this way helps to concentrate on the characteristics of the outer surface of the shape, and the process provides an opportunity to practice visualization. We call these nets. A pattern for a polyhedron is called a net if it has the property that whenever polygons are joined in the pattern, they are joined along a full edge, not just at a vertex. So patterns are useful not only for making models of shapes, but also for determining and finding formulas for surface areas of solid shapes. Recall that the surface area is the total area of the outer surface of the shape. To determine the surface area, we can make or think about how to make a pattern for that shape, and then we can apply the additivity principles for area and add the areas of the component parts to determine the entire surface area. We've got a lot of explorations here. Please don't skip any. Please take your time, and we'll begin with this first one here. So press pause, spend the time here. There are activity downloads in Canvas if you want, so that you can actually check your answers in number 3, printing out all these and then doing them. But for the first 2, you just have to visualize. Press play when you're ready to move on to the next one. In this one, again, you're going to need centimeter graph paper if that download is in Canvas, or you can just do your best on regular graph paper, but go ahead and give these a try and press play when you're ready to move on. Yes, there are lots of explorations in this section because this is all about getting our hands on the nets, seeing how these shapes are created. So go ahead and do this activity. Don't skip any of them. Press play when you're ready to move on. And finally here, continue with this exploration. Don't skip them. Give it a shot. And then press play when you're ready to move to our first example. All right, drawing one net from a tetrahedron made from 4 equilateral triangles. Remember that for a pattern to be a net, each triangle must be joined to another triangle along a whole edge, not just a vertex. So there's actually more than one way to build this net. So if your brain thinks of this differently, you're not wrong, as long as you follow those net rules. So they want a net for this. So when I see I've got this base triangle here, and they're joining up here. So I imagine kind of taking these sides off. If I were to do that, I would have a triangle, and then over here, when this one came down, when this triangle came down, it would look something like that. And when this triangle came down, it would look something like that. When this triangle comes down, it's going to look something like that. That is one possible net for this tetrahedron. You go ahead and give these a try. Press play when you're ready to see the solution. Don't skip them. The downloads will be available on Canvas. And there you go. If a cardboard box, rectangular prism, with a top, a bottom, and 4 sides is W feet wide, L feet long, and H feet tall, then what is the surface area of this box? Find a formula for the surface area in terms of W, L, and H. So we're going to find it for this box, and then we're going to extend it out. So I'm going to draw, and you're just going to see, you don't need to be an artist here. If I can prove that for you, I'm happy to do so. So they say it's W feet wide, and remember, length and width, it's okay, which one, and H tall. So how can I find the surface area? Well, I'm going to look at this in pieces. I'm going to say, okay, I know I need the area of each component, so I need the area of the base, and there are 2 of those. So those areas, 2 of those, are width times length. And then I need the area of this side, and there are actually 2 of those sides with the same dimension, so that's going to be L times H. So I've got 2 of those sides. And then I've got a front and a back. So I've got this front here. Maybe we need a new picture or new color here. This front here which is going to be W, and this height is H, and then I've got one of those in the back too. So plus 2 times W times H. So this could be the formula, right? I can factor out the 2. I don't have to, but it's each of these measurements is times 2. And that is why that formula is valid. So now let's imagine an Egyptian right pyramid with a square base. And we're going to suppose the sides of the square base are 80 meters long and the apex of the pyramid is 80 meters above the ground. Okay, so here we go. I'm going to draw and I'm going to draw this as best I can here, but all right. So, and that should really go to the corner. All right, so we know the sides of the square base are 80 meters long and the apex of the pyramid is 80 above the ground. So they're actually giving me above the ground, not the distance of the slant here, but that's the distance above the ground. So there's a couple different ways I'm going to look at this. If they want the surface area not including the base, that means they want the area of all of these triangles all together. So I know that I've got 4 of those triangles, but I need to figure out those triangles. So I'm going to kind of grab the front of this triangle and see if I can make sense of this. I know that this triangle has a base of 80, but I don't know the height. And again, remember that this here is the distance. It's not this length. This is not 80. I don't know that the side is 80. And also this is what I'm talking about. We don't know this height. And that's this height right here. So we don't know this height, and we could use that, but let's say, all right, instead of taking this side here, let's see if we can actually get this height by looking at this triangle. And now you're really going to need to use your imagination here. But what I'm pulling here is this long side is H. This length here is 80. And then this is half of the distance back. So I pulled this triangle out. Okay, and this is that apex down to the ground. This is H. And this is actually the distance from the ground to that apex. And that's right in the center because it's a right triangle. So I actually know it's half of the length. Remember that this whole thing is 80. So half of this is going to be 40. This one is a really hard one to visualize. So if you need to pause and go back and take a look at it again, I encourage you to do so. So now I can use the Pythagorean theorem here to find H. So this is 80 squared plus 40 squared equals H squared. So that means that this is the square root of 80 squared plus 40 squared equals H. And when I type that in the calculator, I get about 89.4 is H. Now remember, that's this right here. I want 4 of these triangles, not these triangles. These are the sides. So I want 4 of 1/2 base times height. And when I type that in, I get about 3,576 square meters. And again, it may help you to look at this image to see where I got that side triangle out of. So this triangle here is talking about this, and this is a side. So we're going to pause here, and we're going to come back and do a couple more examples.